Good day. Welcome once again to our mathematics live class for this session. Last week we looked over some interesting topics in mathematics, be it algebra, be it calculus, be it trigonometry. We talked about the fact that there were different topics that you had to cover as far as the Jamb curriculum is concerned. Last class we looked at the concept of indices and logarithms, and we also looked at the similarities or relationship that exists within them. For indices, you are talking about the existence of a power and a base, and then you talk about the laws that can govern every operation that exists as far as indices is concerned. However, in the case of logarithms, you are also talking about the existence of a base, but this time with respect to a particular number. And of course, it also has the same laws that also govern the concept of logarithm. We also looked at the interactions or relationship that can exist between indices and logarithms, in which you can also transform an initial function or form into the logarithmic form. We looked at all of this and also took examples to further showcase the initial forms and the logarithmic forms. Of course, in the near future, we will still go back to the concept of indices and logarithms to move further into what we will refer to as initial and logarithmic equations. But for now, that would be the cutting as far as indices and logarithms are concerned. Today, we will be looking at yet another interesting topic. And this one is a topic that is very, very familiar to us, be it in theoretical mathematics, that's mathematics you do in class, or in practical mathematics, that's mathematics you do in real life. This concept is very, very important because it shows you exactly how you can compound or how you can expose or explode numbers, variables, or in fact sums. So the concept for today is arithmetic and geometric progressions. We'll be looking at arithmetic and geometric progressions. In short, we'll call it APs and GPs. APs and GPs are very, very important because they show a regular pattern of numbers, of letters, or variables, as the case might be, and show exactly how one number relates to another, how the second number relates to the third, how the third relates to the fourth, and so on and so forth. We will break all of this down within this class and then also pick different kind of questions to show exactly how we utilize arithmetic progressions and geometric progressions. Now let's begin with the very first one. Now, whenever we talk about the term progression, we are talking about a sequence of numbers or a sequence of variables that follow a certain pattern. A progression is a sequence of numbers or variables that follow a certain pattern. That pattern governs all the numbers within the sequence or all the variables within the sequence. That is a very, very important fact. Now, for the arithmetic progression, it is saying this sequence is governed by an additive term. Arithmetic progression is talking about a sequence that is governed by an additive term. Now, how exactly do we write that kind of sequence? The first term of the arithmetic progression is usually denoted as A. That is the inception. Yeah? Now, from this inception, we would now combine or extend it to the second, to the third, to the fourth, fifth, sixth term, and so on and so forth. For the arithmetic progression, this sequence is extended using an additive term. That additive term is what we refer to as the common difference. usually denoted as D. As far as the arithmetic progression is concerned, A and D are the most important values in the progression. Now, how do we use them? Generally, we can write the sequence as A, which is the first term. To get the second term, we will add the common difference to the first term. To get the third term, we will add the common difference to the second term. So we see how that progression works. To get the next term, we will add the common difference to the previous term. And so on and so forth. Of course, if we write it simply, this will be what? A plus D, A plus 2D, A plus 3D, and so on. What do you notice? All these sequences are governed by the common difference. These sequences increase in value based on the addition of the common difference to the preceding term. So where you have the first term, add the common difference to it, you get the second term. Add the common difference to the second term, you get the third. Add the common difference to the third term, you get the fourth. Add the common difference to the fourth term, you get the fifth, and so on and so forth. That is the progression that we have. Now, it now begs some very, very interesting facts. This is the first term. This is the second term. This is the third. This is the fourth. What the therefore means is that we can generalize this and look for the nth term. Nth term means what term or what value would be at any term we decide to pick. So let's say we pick the 10th term, what would the value look like? Let's say we pick the 20th term, what would the value look like? Let's say we pick the 50th term, what would the value look like? Generalizing that will give us a concept called the nth term. Now, how do we write the nth term of an arithmetic progression? Generally, if you notice, when you had a second term, you only added one common difference. At the third term, you added two common differences. At the fourth term, you added three common differences. The pattern you notice is that as the terms continue to increase, the number of common differences you also add continue to increase. And it's always one lesser than the term we are looking at, which means for the third term, we added 2 times the common difference. For the fourth term, we added 3 times the common difference. That is 4 lesser than 1, 3 terms. 3 less than 1, 2 terms. 2 less than 1, 1 term. Which means that if we were to look for the nth term, following this same pattern, I would be adding n minus 1 times the common difference, which is 1 less than the term I'm looking out for. So if n was 4, I'll be having 4 minus 1, which is 3. If n was 50, I'll be having 50 minus 1, which will be 49, and so on and so forth. This n term has different symbols, usually written as L subscript n. So we have the first term of the arithmetic progression, the common difference of the arithmetic progression, and again the nth term of the arithmetic progression. And from the nth term, we can generate one more variable, which is n, which will now denote the number of terms. So this gives us an idea of every single important value that we have to cover as far as arithmetic progression is concerned. The first term, which is the inception, the common difference, which is the term that is added to each of those sequences. So for the first term, I add the common difference, I get the second term. I add the common difference again, I get the third term. I add the common difference again, I get the fourth term, and so on and so forth. I can now generalize this concept to get the nth term, which is the term at any value it is, whether it's 50, whether it's 51, whether it's 85, and so on and so forth. So we have the nth term, and from the nth term we can bring out the concept of number of terms, which is how many terms exactly am I counting at. So if I have 50 terms and I'm looking for the 50th term, that means my n will be equal to 50. If I'm looking for the 45th term, that means my n is equal to 45. If I'm looking for the 1000th term, that means my n is equal to 1000, and so on and so forth. So this gives us the identities that are very, very important. And this formula, ln, which is equal to a plus n minus 1d, is a very, very important formula in the field of arithmetic progression. Remember, arithmetic progression. We move forward. Now we have looked at arithmetic progression. We have the formulas. We are going to take the examples in bulk so that it's easy and we can also see exactly how it works. But now we have looked at the formula. We now also have the term called the geometric progression. So this would show you exactly what makes them unique. We said that for the arithmetic progression, it was a sequence that was governed by an additive term. The additive term was the common difference, and we have seen exactly how it works. For the geometric progression, it is a sequence that is governed by a multiplicative term. Unlike the arithmetic progression where we are adding, for the geometric progression we are multiplying. So how does it work? First, of course, we'll have our first term. That's the inception. Let's call it A. And this time around, we will have a term that governs the geometric progression. And that's the multiplicative term. In this case, we call it the common ratio, denoted as R. The common ratio. And with these two important terms, we can now have a glimpse as to how exactly the sequence looks like. If I have the first term in the sequence, whenever I multiply the first term with the common ratio, I will get the second term. Whenever I multiply the second term with the common ratio again, I will get, so let's write it this way so it's clearer, A times R. Whenever I multiply the second term with the common ratio again, I will get the third term. Whenever I multiply the common ratio with the third term, I will get the fourth term. And so on and so forth. So if we combine this, what would we have? A, AR, AR squared, AR cubed, and the list is endless. So what do you notice? From the first term, if you multiply by R, which is the common ratio, you get the second term. If you multiply by R again, you get the third term. If you multiply by R again, you get the fourth term. If you multiply by R again, you get the fifth term, sixth term, and so on and so forth. Again, this is the first term. This is the second. This is the third. And of course, this is the fourth, and so on and so forth. What do you notice? Just like the AP, where the number of times we multiply the common difference, or the number of common difference we are adding up, was one less than the term, the same concept happens here. The power on the common ratio is always one less the term. So when we are adding the third term, we had 2 as the power. When you have the second term, we have 1 as the power. When you have the fourth term, you have 3 as the power. What this means is to generate the nth term, this time around, we will now have n minus 1 as the power. That's 1 less than the term. In that case, we'll have it to be a r raised to n minus 1. And this is called the nth term, also denoted as ln. And from there again, of course, number of terms, which is n, is an important identity. So what do we notice? For the arithmetic progression, we add. For the geometric progression, we multiply. These are very, very important concepts. Now, it also means that the first most important formula for the geometric progression is this: AR raised to the power of n minus 1. That is for the arithmetic progression and the geometric progression. Now, a question now arises. And what question is that? The question is, now we have looked at how the sequences look like. That's the sequence of the arithmetic progression and the sequence of the geometric progression. What now happens when I decide to add all these individual terms together? Right? So I have the first term, comma, the second term, comma, the third term, comma, the fourth term. What if I'm adding the first term plus the second term plus the third term plus the fourth term? Same thing here. What if I do the first term plus the second plus the third plus the fourth plus the fifth and so on and so forth? The process of adding the terms within a sequence together gives rise to what we call the series. When you add each individual term of the sequence together, you get what we call a series. And so at that point, we can also discuss what we also know as the arithmetic series. Right? The arithmetic series is simply the sum of the sequences, the sum of the members of the term in the sequences. That's basically what the arithmetic series is saying. Essentially, we are saying A, which is the first term, plus the second term, plus the third term, plus the fourth term, and we continue adding on and on and on. Now, if you have noticed, the three dots I'm always using, they are called ellipses. Ellipses, which means that you are quoting the fact that there is the existence of an infinite number of terms after that point, right? But they are so much that you really do not want to waste time writing everything, right? So when you have so many terms after a point and you want to shorten it, then you can always use the ellipses. For instance, let's say I want to write 1 to 100 and I write 1, 2, 3, 4, 5, and I decide to use the ellipsis and go 99, 100. This is a very, very important use of the ellipsis as well. Why? Because if I wanted to write it without the ellipsis, I would have had to write 1 to 100 with all the digits. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all, every single thing. However, by using the ellipsis, I am saying within 5 and 99 that I did not write, there are a lot of values in there that take this same structure, right? So because on the first side I've already seen a couple of numbers, I can already guess what will come next after 5. 1 followed by 2, followed by 3, followed by 4, followed by 5. I expect it to be followed by 6, followed by 7, followed by 8. So because I already have a pattern, by writing this ellipsis, I'm saying, yes, that pattern continues into those numbers I did not write. And then at the end, you are going to get to 99 and then to 100, right? So you use an ellipsis when it's finite to showcase the middle part where you did not write. And then when you use the ellipsis in this form, it's infinite, which means you don't really know where the sequence is going to end, but you know exactly that the sequence is going to follow this same pattern. Those are very, very important identities. Now, for the arithmetic series, which is the addition of the terms of the sequence, don't forget, we are just adding the first term to the second term to the third term to the fourth term. What it also means is that we can now find the sum of the first few terms that we decide to add together. So I can say, let's find the sum of the first 10 terms, or let's find the sum of the first 20 terms, right? Because we are summing them together in a progression, right? Because first term plus the second term plus the third term plus the fourth term, we are summing them in that progression. which means I can take the sum of the first 2 terms, which will just be these 2. Sum of the first 3 terms, which will just be these 3. And then sum of the first 4 terms, which will be these 4 terms. And so on and so forth. By that mean, it means that we can generate the formula for the sum of n terms of the arithmetic series. What this means is, what if you don't know, you are just trying to arbitrarily see what the sum would be. Let's say sum of the first 500 terms. How exactly are you going to take that? By using the formula, it becomes very, very easy. And what's that formula? The sum of the first n terms is given to us as n divided by 2, all into bracket 2a plus n minus 1d. This is a very, very important identity for the sum of the first n terms of the arithmetic series. Another way of writing this formula is to write it as n over 2 into bracket a plus ln, where ln, of course, is the nth term. Not the last term, the nth term. That is a very, very important identity. It is never the last term, it is the nth term. So let's say we even have a progression that is just 5 terms, right? Then the 5th term is your last term. However, it is important that you utilize it as the 5th term rather than as the last term. The formula tells you that you should use the nth term. In some of our examples, you will see exactly why it is very, very important to point out this fact that you are dealing with the nth term and not the last term. So this is the formula for the first n terms of the arithmetic series. You can either decide to use this, or you can either decide to use this, right? So the denominator must always be positive whenever we are dealing with the sum of the first n terms for a geometric series. So if r is greater than 1, you can just carry out this simple inequality, send 1 to the other side. You would have r minus 1 is greater than 0, which means that r minus 1 is positive. So that gives you an idea that r minus 1 will be the one in the denominator. Using that same value in the denominator, all you just have to do is clone it in the numerator, which means r minus 1, also r minus 1 in the denominator. Only difference is the r to the power of n. That's all. In the case of r less than 1, r less than 1 simply implies that 1 minus r is greater than 0. Or you can see it as 0 less 1 minus r. Anyone is fine. But what it means is that 1 minus r is positive. So 1 minus r is what we use as our denominator. And by extension, we carry that denominator and also clone it in the numerator and then raise r to the power of n. That's basically how we generate these formulas, right? And it's very, 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 very important that we keep those formulas in mind. So we have seen the formula for arithmetic progression, which is when the progression is governed by an additive factor, which is the common difference. In this case, where we have the first term and we add the common difference to it, you have the second term. Add the common difference to the second term, we get the third term. Add the common difference to the third term, we get the fourth term, and so on and so forth. And then we can generalize into the nth term as a plus n minus 1d. Similarly, in the case of the geometric progression, this time around the sequence is governed by a multiplicative factor, which is called the common ratio. This time around, if you have the first term and you multiply it with the common ratio, you get the second term. Multiply with the common ratio yet again, you get the third term. Multiply with the common ratio yet again, you get the fourth term, and so on and so forth. And then we can generalize this by comparing the power of the common ratio and the term to give us the nth term. And then for the arithmetic series, we are saying that if you add the individual terms of the arithmetic progression, you will get the arithmetic series. So by adding them, we can now take the sum of the first n terms of the arithmetic series, which is sum of the first 10 terms, sum of the first 20 terms, and so on and so forth. And the formula would be n over 2 into 2a plus n minus 1d. And you can shorten it by using the nth term as n over 2 into a plus ln. And you can verify, yeah? Let's take the first two terms here. If you had to add this together, you'll be getting